Okay, so last time we looked at the machine learning fundamentals and we started looking at very basic algorithms. And later we also look at the software part of this, which is WEKA. So today we are going to continue. Mainly I'm going to discuss other machine learning algorithms. Mainly I want to discuss decision trees. Okay. So last time we discussed what machine learning is, and basically we want computers to learn from when we provide the data. Basically, the area of machine learning focus on improving the performance of various learning algorithms. And we discuss various different definitions for machine learning, as well as sample examples of outcomes of machine learning algorithms. So here we have observed outcome of a decision rule as a rule. So the output is actually a set of rules provided the data. And today we are going to see how to create decision tree like this given data sets. Right. And this is another example where we want to predict some numbers. So the idea is how do you, learn from that? And that's what we have been discussing. And there are a lot of applications areas and quite popular nowadays. I hope the techniques we learn in this part will be very useful for this. Right. Now, having said that, last time we look at basically 0 and 1. And that's what we are going to continue today first. With the 1R, what we discuss is actually generating what we call the single level decision tree. The main assumption under this is just one attribute enough to make a decision. So therefore, what we do, we go through each and every attribute at a time. So that's what we have done with the 1R. With the weather data set, the sample toy problem, when we go through each and every attribute, creating a rules based on comparing their frequent classes, creating a rule for each different attribute value, we can calculate individual errors and the total errors. The final outcome is actually very simple. We are going to select attribute which gives us the least amount of errors. In this particular case, we had 4 attributes and we can choose either outlook or humidity. And the output, as I told you earlier, you select just one. So in this particular case, I have chosen outlook attribute. And then whenever you get a new day, you just have to focus on the outlook attribute. If it is sunny, we know the prediction is no. If it is overcast, it's yes. If it is rainy, that is again yes. So this is what we have discussed last time. Right. So let's start the first new theory part. Okay. Now, if you compare our data set, what we have observed is we had a categorical data. What I mean by categorical data, meaning like you have just labels. Outlook, we had sunny, overcast, rainy, temperature, high, cool, and so on. So these are just the labels we had, means sometimes called nominal attribute. But what about if we have numeric attributes? That's what we are going to do. So simple one way to handle this issue is you can actually identify some range of values and we can follow the same procedure as earlier. Right. And then the problem is how do you find these ranges, right? So that's what I'm going to discuss first. Right. Now let's look at this new data set. Okay, there's a small issue with here. Part of the data is not available. Right. Now let's, I will take one attribute and you are going to work with the next attribute. So listen carefully how we are going to do this. Right. Now, this data set is slightly different from our previous data set. If you compare here, we have two numeric data set, temperature and humidity, we have numbers. So when we have numbers, we can't follow the previous algorithm, right? Because there's no, values we can find out. We don't have any categories. So therefore, what we are trying to do is we are trying to find ranges. So when we find the ranges, one technique, what we are going to do is we'll take, for example, let's take temperature. We'll sort all the attributes in the ascending order. So you can notice that the lowest value in this group is 64. Then the highest value is 85. So you can see we have sorted in ascending order. And then for each value, we will also note down their labels. So when you have 64, it's yes. Similarly, 85, we have no, right? And then, so we are going to find out the ranges, right? So therefore, whenever there's a class change, we'll make a breakpoint, right? So you can see between 64 to 65, we have a change of classes. So we put a breakpoint. 65 to 68, again, there's a change, we put a breakpoint. And then we continue like this, we put a breakpoint, right? And then here also there's a difference, but we can't put a breakpoint because it's the same number, right? So therefore we shift it and put a breakpoint because we want to anyway, there's a change after 72. So we want to put a breakpoint, but we shift it because we have the same numbers. And then we have yes, there's a change. Okay, breakpoint, another breakpoint, and so on. Now, this is good, but the problem is from these algorithms, what we expected is we want to predict for unseen data. And when you have new data or unseen data, you will not have the same distribution. So therefore, if you put a breakpoint like this will exactly represent your data, right? This is not good. So therefore, this is too many breakpoints. So we want to simplify this, right? So the idea of, exactly representing your training data in machine learning, we call overfitting. So overfitting means, we will learn this later on again, that you will get very good accuracy from the training data, but when you apply it for new data, you are getting a very poor accuracy. So this will happen if you are taking each and every breakpoint like this. So therefore, one technique of, avoid the overfitting, that means it's very sensitive, the change of classes. So we are going to enforce minimum number of instances from the majority class. What I mean by this is, if you look at the numbers earlier, what we had is, in a range, we can even have just one attribute. Instead of that, we are going to specify we are going to specify at least you need to have this many number of instances. So in this particular case, we are going to say that, okay, you have to have at least 3. Now, if you say 3 is the minimum number, so you can go through this. So you can go through this. So here is a breakpoint. So you can remove this because you have just one attribute, right, from majority. Now, if you look at this one, you have like 2 instances, one from each. You remove this one as well. So when you remove this one, okay, now this is better because you have 4 instances from the class yes and 1 from no. So you have at least 3 from the majority. So you can take this as a breakpoint. And that's what we are going to do. So we are going to take this as a breakpoint, and the majority is yes. Similar to that, if you go through each and every, here we have 2 and this is 1. So we'll remove this. Now what happens? We have 3 and 2. So we have 3 from majority. We can take this one also as a breakpoint. Right. Now, if you continue this, you have to remove this one. You have to remove this one. Unfortunately, these are the only attributes we have. So you have 2 from each. Right. Now let's look at the majority. This was yes. And this is also yes. This is yes and no equal, but since we have the previous ones are only yes, we can use no. So now, since we have the same values for yes, you can remove this part as well. So the only breakpoint will be between these two numbers. You can see this part will be yes, this part will be yes, and this part will be no. So what we are going to do now, okay, we'll take a majority point, that means, sorry, middle point. The middle point is 77.5. You add these two numbers and divide by 2. And if the temperature is less than 77.5, then we can say the outcome is yes. If it is greater than that, we can say outcome is no. Right, now that we said this, we can now calculate the table. So you can notice here, temperature value, right? We are getting, if it is less than 77.5, it's yes. If the greater than 77.5, it will be no. So you can notice here, right? When you calculate the number of yeses here, we have 1, 2, 3, 4, 5, 6, 7. And then we have 1, 2, 3 no's, right? So we have 3 out of 10, here 2 out of 4. So we will have 3 out of 10 and 2 out of 4. That is total is 5 out of 14. Right. Now, can you do the same for the humidity? Now, this is for humidity. What we have done is we got all the numerical values sorted together with the outcome play. So now we can make breakpoints, right? So when you're making a breakpoint, let's first do as previously. We can make a breakpoint whenever class changes. This is okay, right? There's a class change, but you cannot have a breakpoint here, right? So therefore, immediately after that, we'll put a breakpoint, right? And then after this, here you can have a breakpoint. And then, yes, here we can have a breakpoint. Values are different. Again, here also we have a breakpoint. Okay, there's a class change. So anyway, we have to put a breakpoint. And here also we have to put a breakpoint. This is if you specify breakpoints whenever class changes. But then we discuss whenever you want to specify minimum number, then you can remove some of these breakpoints. Let's assume that, okay, we'll say minimum of 3 from majority class. If that is the case, if you start from the beginning, here we have one instance, we have to remove this breakpoint, right? Yes, remove. Now what happens? Okay, we have 3 yeses, isn't it? So we can keep this breakpoint. And what about here? Here also we have 3. So we can keep that one as well. Okay, we can start from here. Okay, we have to remove this one because there's no 3 from the majority. We have to remove this one as well. There's again, there's no 3 from the majority. So we have to relax this one as well. Now we have 3. And finally we have yes. Okay, here are the values. Now let's go through. In the first interval, we have majorities yes. Second interval also we have majorities yes. So there's no point of this breakpoint. We can remove that. And this is majorities no. Again, this is yes. Okay, so we have 2 breakpoints. So what are the values? 80 and 85. So if the value is less than or equal to 82.5, the majority is yes, right? Then greater than 82.5 and less than 95.5, We know the majority is no. And finally, if the value is, we'll use equal sign. If the value is greater than 95.5, then we can say it's yes. Okay, now let's calculate the accuracies. When the value is less than or equal to 82.5, we said output is yes. So there's a one negative instance. The error rate is 1 out of 1, 2, 3, 4, 5, 6, 7, right? And if it is in between, when we say no, you can notice, okay, there are 2 yes instances out of 1, 2, 3, 4, 5, 6, right? And here you have no errors because we have just one attribute. So the total error, right? The total error is 3 out of 14, right? 3 out of 14. Okay, so if you go back, and this is exactly what we have observed. The humidity ranges are, if the value is less than or equal to 82.5, it's yes. And greater than or equal to 82.5 and less than or equal to 92.5 is no. Okay, there's a small mistake here. It should be greater than 95.5. It should be yes. And the outcome is 3 out of 40. Right. Given this, if you examine the attributes and their errors, we have to select the attribute with the lowest error rate. So in that particular case, we have to select humidity as the final outcome. So therefore, for the second data set we have observed, when you apply 1R, this is the outcome. So it select the humidity as outcome. And here are the values, right? So in this particular case, it's correct. So we can see that when the humidity is less than or equal to 82.5, so we are going to predict it as yes. If it is in between 82.5 and 95.5, we are going to predict as no. If it is greater than 95.5, we are going to say yes. Right. Okay. Right. So let me show you this outcome in the WEKA software. And remember last time we started with the Explorer. When you click the Explorer, we will get an interface to work individually. So let me open the file. So my case, it's saved inside the C under program files. And then I will go inside the WEKA folder and there's a data set. Okay, observe that there are 2 data sets, whether nominal, which is all the categorical values. But this is the data set that we have observed today with mixed data. It's called weather numeric. So let me click open. Okay, you can observe the attributes. Let me show you the data set. I'm going to click edit. And you can observe that, okay, temperature and humidity attributes are given in numeric attributes. Okay, now when you observe this side, you will see the attributes and you see the visualization here. So Outlook, we had nominal values. We have 3 values as sunny, overcast, rainy. It will give us the counts. And then it will also show in 2 colors. The 2 colors are for the play, yes and no. If the play is yes, we have blue color. If the play is no, we have red color. So in Outlook, you will observe that when we have Outlook sunny, we have 5 instances. 3 is no, 2 is 1, 2 is yes. Overcast, we have 4 attributes. All the 4 attributes are yes. And then rainy, again, you will see 2 no's and 3 yes. So now let me show you numeric attributes, and it's slightly different because you have numerical values. It will show you some statistics. Basically, since it's numbers, it will show us the minimum and maximum values as well as mean and standard deviation. Similarly, you can observe the same about humidity. Windy, again, back, it's categorical nominal data we have. And finally, we have play. Right. Now, to do the classification, we have to go to classify tab. Okay, we have to choose 1R. So this is 1R. And remember, there's a parameter here. It's called B. It's called mini bucket size. This is the minimum number of instances we are going to specify. So let me put 3 because we selected at least minimum of 3 instances from the majority class. So you have to make the bucket size 3. And if you click OK, now you can observe that it shows you the algorithm as 1R with B3. That means we are specifying minimum number of instances in the majority as 3. So let me click start. And when you click start, you will observe the outcome. Okay, it says classify a model, and it says the answer is humidity. Right. Okay, we have finished very small machine learning algorithm, 1R. Okay, let me move to the next one, decision trees. Okay, decision trees are quite common, and they are actively used in machine learning community as well. So what is a decision tree, right? So in this part, we are going to discuss how we can learn a tree-like a structure from the data, right? So when we say a tree, what we have is just attributes and their values. So we take attributes as nodes in the tree, right? Nodes in the tree. And the branches, we will use the values, right? So how do you build this? There are many ways of building this, but the quite commonly used technique is called divide and conquer, or we call top-down induction of decision tree. So what basically it does, given a data set, it goes through each and every attribute and select a best attribute. You select an attribute to put in the root node as the top of the tree. And once you put in the root node, then you will get the branches. And then after you will get branches, you are trying to fit other attributes. And by repeating this process, you are trying to create a decision tree. That's a simple idea. Okay, so let's see, right? Now, one of the issues is when we have attributes, which one we are going to select? That was the question. Okay. Okay, so in this one, what you notice here is for each attribute, you can notice Outlook, we have 3 values. We have create branches, sunny, 1 branch for sunny, 1 branch for overcast and rainy. And in here, the leaves, what you notice is the already available instances, how it classified when the Outlook is sunny. So we have 2 instances classified as yes, 3 instances classified as no. When Outlook is overcast, everything is classified as yes. When Outlook is rainy, then you will see the 3 instances classified as yes, 2 as no. So similarly, you can see temperature, humid, and windy. The question is which one you are going to select. Okay, any attribute can be taken as a root node. That means we can select an attribute and random. So then whatever the tree we build called a random trees. Actually, there's a algorithm called random trees which you can use. So we can use any attribute to put in the root node. But there's in literature, you will find that many prefer simpler trees, right? Remember, we mentioned in the very beginning, simple machine learning algorithm works well. So we can work for simplicity. If that is the case, in our case, we can see here, right? If you take the Outlook attribute, it will purely classify through the overcast. So which means that we are not going to expand the tree in this branch because it stopped at this point. There's no point. So therefore, if you are focusing on pure separation, we call purity, then we can select Outlook. So in this particular case, we have decided to use purity. So separating attribute values pure as much as possible. Based on that criterion, we can select Outlook as the root node. Right, that's the first step. So if you select Outlook as a root node, you have to repeat the process, which means that in this branch, we are going to finish it. But in here, we have now 5 more instances. So we have to put another attribute and see. Right? So as I told you earlier, finding the best attribute, we are going to make it to a smallest decision tree. So the idea is we are trying to produce with the purest nodes. So the popular selection criteria is called information gain, right? So that's what we are trying to do. So we can measure something called a measure of impurity, and then we can use impurity measure for this. So if you follow the same steps, then what happens? You are getting the Outlook attributes as the best one. So let me go through the next step first. So you get the Outlook, right? Then what happens? The next step, you are trying to find the next attribute. Which one is the next attribute you are going to put in? So since you have selected Outlook attribute as a root node, from the left branch, when Outlook is sunny, we need to find out which attribute to put in in the branch. So 3 possibilities here. You can notice we can put temperature, humidity, and windy. And we remember that there were 5 instances came to this branch. So if you follow the same idea that we have discussed earlier, if you look at pure separation, you can observe that the humidity is the best attribute which purely separate the attributes, and we can stop at this point. And then if you repeat the next step, what is the next step? Now we have temperature and windy. You can put temperature and windy in the other branch and you can check. And you will notice that when you put windy, it will purely separate. And this will be the final decision tree, right? So now let me show you this in the WEKA. So I'm going to open up. And then let me click Explorer. Right, let me open this time. The data folder. Let me select weather nominal. Right, and I'll go to classify. Okay, there are many decision tree algorithms. You have to go to trees and then you can select. Okay, I'm going to first select ID3 and this is what I have described, and then I'm going to show you the J48. Okay, let me first click ID3, and when you click start, okay, you will get a decision tree here in the text form. In ID3, we can't visualize, so I can not show you as a tree structure. But then let me choose the next one. It's J48. I'm going to discuss the differences later on. The second one, it looks the same outcome, but if you right click on it, you can visualize the tree structure. Can you see the tree structure here? So we can see Outlook is on the top. And if it is sunny, overcast, rainy, after sunny, we put the humidity. I hope you remember this one as well. And what I said is if you put windy, it will purely separates. And this is the outcome. So if you can't find ID3, there's a reason for this. There's something called package manager. Yes, if you go to tools and if you find package manager, so some of the algorithms are not included and you have to separately install them. So let me go to tools and package manager. Okay, so you will get some interface like this. Right, after you got this, type ID3. And then when you click ID3 and press enter, you should see. So what I'm trying to find out. We need to install it. Let me check. If you can't find ID3 in your WEKA installation, you can go to the package manager and you can search for simple education learning schemes. This will install education machine learning algorithm like Prism, ID3, IB1, and simple naive base. You click then you say install. And once you install it, make sure that you close, right? And then reopen, right? You have to start from the beginning, reopen the WEKA and then observe. So let me, in this my case, reopen it. You can go to explore again. We are going to open the default data comes with the WEKA installation. So under the WEKA folder, you can find data folder. I'm going to select with the nominal first. You go to classify, click classifier. Now under ID, under the trees, you should see ID3. Now click start and you should observe the outcome like this. Okay, with that said, let's go back to the theory part. Let me briefly go through the mathematical basis for this. So selection of attribute, visually it's okay for small data set. But when you have a very complex data set, let's see how we can identify attributes which purely separates the data. Now, the idea of selection of attributes mathematically goes down into calculating information. So this is based on the calculation of entropies, and the probabilities here, although we see probabilities here, these are based on the number of counts that you have seen. So for example, when we have outlook is sunny, we had 2 positives and 3 negatives. So 2 out of 5 and 3 out of 5 and so on. So we can calculate this, and this is the equation we are going to use calculating the entropies. So when you use the log in base 2, what you are getting is the output is in bits. And what we are trying to do here is we are trying to maximize the entropy. And entropy is maximum when you have classes are equal likely. But entropy is minimum when you have just one class, right? So that's what we are going to use here. So here is how we are going to do this. So we are going to calculate something called information gain. And first of all, you have to calculate the information. This is what we have observed earlier in entropy, given the data. So we will calculate the information, and then based on the attribute, you will get different branches. So as a proportionally, you are going to calculate the information, and then you get the difference. So this is like before you split the data, you calculate the information. Here you will calculate the information after the split from attribute, and then you get the difference. And this is what we call the information gain. And this is the criteria we use to select the attribute. So in this particular case, let me show you the calculation for Outlook is sunny. I hope you remember that in Outlook is sunny, right? In the sunny branch, we had 2 yes and 3 no's. So in this particular case, the entropy, we have P1 and P2 is 2 out of 5 and 3 out of 5. So entropy P1, P2, we can expand using minus. Assuming this is P1 and P2, we can say P log P, and this is P2 log P2. So this is how we are going to calculate. And when you solve this in bits, we are getting 0.971 bits. Similarly, you can also calculate the for Outlook overcast and Outlook or rainy, and these are the values, right? And then if you take the expected information for the attribute after you break for the Outlook, so that means when Outlook is sunny, Outlook is overcast, Outlook is rainy, you will get proportions. What I mean by proportions here, meaning like when you separate the data, you will get 5 instances for Outlook sunny, 4 instances for Outlook overcast, 5 instances again for Outlook rainy. So you will take proportions, and this will be the information after you split based on the Outlook attribute. Now to calculate the gain, you have to calculate the information before the split, information after the split. When you calculate before the information, you will get 0.940. After split, you will get 0.693. And the difference is the gain for Outlook. We will get around like 0.247. So in similar way, if you calculate the gain for all the attribute, here is how it look like. Observe that we are getting the highest information gain with Outlook attribute, and that's the reason why we can select it. So since we have the highest information gain coming from the Outlook, we select the Outlook attribute, and then you repeat the same procedure with when you split further. So that is a mathematical basis for choosing information gain to select the attributes for the root node. Right, and similar way, this is what you have observed after you select Outlook. Here it will calculate the gain when you separate with temperature, humidity, and windy. And here also you can observe humidity which purely separates. Therefore, you will get the 0 In this particular case, if you calculate the entropy, it will be 0. So the difference is maximum, right? Therefore, the humidity is the best attribute to select in this particular case. Right. So I hope now you have understood about how to get a tree structure from the data. And we discussed in very briefly on theoretical basis as well. So let's continue. There are few things that we need to discuss. Now, there are some issues of these measures as well. One issue is when you have ID-like attribute. For example, let's say your registration number, right? Or your passport number. When you have unique attributes, you have a bit of a problem. Why? Then you will have large number of branches and they are pure separations. So ideally, if you calculate the information gain, then these attributes are automatically selected. So therefore, this should be noted, and ideally, most of the time, we should remove them before we build the tree structures if you have any unique attributes. Right, now to overcome this problem, sometimes when you have highly branching attributes, people have devised another measure called gain ratio. What basically it does is actually divide by the intrinsic information, similar to accommodate when you have low values, right? If you have highly branching attributes. So in this particular case, if you have an ID-like attribute, still we have this issue. You are not getting any update from this, but if you see in the outlook, if you calculate the gain ratio in this particular example, it shows you how to find this. So to get the gain ratio, what you do is you first calculate the information gain. This is the number we have observed early. And then you can find out the information in that branch we call intrinsic information. And then you divide these two numbers to get the value for gain ratio. Even at a gain ratio, you will observe here gain ratio, if you focus just this number, you will still see that Outlook is the best, right? But remember, Outlook had 3 branches. Therefore, you will get very high values. Split information will be normally very, very, very high when you have a large number of branches. But when you have small branches, it will be low. So that's how it actually handles. But in this particular case, irrespective of number of branches, you will observe that Outlook get the highest the gain ratio. And if you are selecting gain ratio, it will be the same. So there will be no changes in your decision tree structure. Right. Now, what we have observed is if you use gain ratio is also come up the top, and you will not get any improved accuracies if you have ID-like attributes. So ideally, you should remove that if you have unique attributes, right? And that's what it bases in C4.5. So we have observed that 2 algorithms, ID3, that is the basic algorithm. And C4.5 is actually more advanced one. That's what you have observed as J48 in the WEKA software. Right. There are many other measures as well. Now we are going to do, machine learning in Python as well. And I will show you there. When you're building a tree structure, they are using something called Gini index. The equations are very similar to the previous one. When we have entropy, instead of using minus P log P, they are using minus P squared. That's all. So you will get something called 1 minus P squared, and that's what we are going to use in the Gini index. And the find in the impurity also the same. You will calculate the Gini value before the split, and you will calculate the Gini after split, and you get the difference. And this is the basis for card trees. There's a decision tree algorithm called card, and this is the mathematical basis for that. Right. Now, I told you we have different tree structures, and we have observed there's a tree structure called ID3, and there's a tree structure called J48. There are some differences. If you want to extend the algorithm for numerical attributes, missing values, and generalize the model, that means you want to apply for unseen data, then the ID3 is not enough. So let me briefly explain how in WEKA, the improved version of decision trees, but is J48, what we have observed, how they handle the numerical attribute, missing values, and also how do you generalize the model. Okay, the first of all, extending tree, what we have discussed is assuming that your data set is nominal data. Now we have to extend this to handle numerical attributes. The problem with this one, with the numerical attribute, is when you want to calculate the entropy, you have to calculate for each and every value, which is problematic, but there's no other way that we can do it, right? So therefore, what you do is you go through, like in 1R, you sort it out in the ascending order, but you are going to make a split in each and every place, and then you can calculate the information gain or gain ratio, right? And then you will find the best split point, right? So I'm going to show you one example. If you select the temperature numeric attribute, and this is what we do. Basically, you will sort it out. And then in this example, we are selecting 71.5. That is, you are putting a breakpoint here. So similarly, you are going to breakpoint each and every place, and you are calculating the information. In this particular case, as an example, we put the breakpoint in between here. So what you notice is we have 1, 2, 3, 4, 5, 6 instances there, right? So 4 yeses and 2 nos. And after that, you will have 5 yeses and 3 nos. So you can calculate the information like in early, and you can calculate the gain ratio. So you will find the best value, right, by evaluating each and every breakpoints. Right. The next question is, how do you handle missing value? So if the value is missing, and if it is a very significant branch, then better you will create a separate branch and say it's missing, right? Or else you can actually make it a split, the data. Right. So now we have discussed 2 things. Now let's look at how to generalize the tree. Generalization here means we are trying to simplify our model so that we'll get better accuracy when you have new data. So there are 2 ways of simplifying trees. We can remove some of the branches in the trees. So there are 2 techniques we can follow. One is called post pruning. That means you develop the whole decision tree and then remove some of the branches in the down. Or we will have pre-pruning. We can decide how many, what are number of depths we are going to use. The problem with this one is, like, sometimes you might, finish it early. That might be an issue. So basically, in practical applications, we prefer the post-pruning, meaning that we fully develop the decision tree and then we remove some of the branches. Right. Now let me show you some of the post-pruning techniques. I'm going to show you like 2 techniques, subtree replacement and subtree erasing, meaning that removal of branches. Okay, observe this small program, small tree. And if you look at this particular branch, okay, maybe I will select the branch, focus on this branch. So if you look at this branch, majority of the labels say bad. So instead of this branch, you will observe we replace this branch with the classification of bad. Yes, I know that there are some instances classified as good, but majority of the time it's bad. So by doing this, what we did is our tree is simplified. This is called subtree replacement, meaning that the branch is replaced with just outcome, right? So that's what we call the subtree replacement, simplifying your trees. Okay, next one. The next one called subtree erasing. What I mean by this is when you have a tree structure like this, you remove B. You delete this part and then you connect C to A. So when you connect C to A, you know that attribute numbers will be distributed, right? And this is what we call the subtree erasing. So the two techniques that you can actually use, right? Let's move on. Now with this, we are going to finish our discussion of decision trees. Let's look at the things that we have discussed. So there are many ways of developing decision trees, but we have discussed how to develop from top to bottom. This is called top-down induction of trees. So the basic algorithm is called ID3, and that's what we have discussed earlier. And in default tree development, people have used a measure called information gain. So there we calculate the information before the branch and we calculate the information after the branch. But there are some problems when you have large number of branches, then there is a proposal using gain ratio. So the basic algorithm is called ID3, the extended version called C4.5, which you can actually handle numerical attribute, missing values, and any noisy data, right? And in parallel to the decision tree, there was another tree structure is common in the decision trees called cart. And remember, we discussed an measurement called Gini index, and cart uses the Gini index. Right. But remember that there could be many more. So we have looked at information gain, gain ratio, Gini index, but there could be many more. One, there are measures like chi-square we can use for selecting the root node. Right. So that's about the tree structures. Right. So let me move on to another machine learning algorithm. Right. Now, what are the things we have discussed so far? We discussed about 0R, 1R, and decision trees. Under the decision tree, I briefly described about two decision trees, ID3, C4.5. Okay, the next algorithm. Now, in this next machine learning algorithm, basically, it will generate rules, if-then rules. So what are the ways that you can actually create rules? One way is simply you can actually build a tree and then convert it to a tree. So it's easy, right? So let's do this as an exercise. So I'm going to select the decision tree that we have built early, right? And then please give me the rules. Okay, so here is a decision tree. Give me the rules. Okay, let me give you a easy rule. So I'm going to write down the rule. So one rule, I can go through the root node. I can start from here. The attribute is outlook. If outlook is overcast, we know the classification is yes. So I can write like this. I can say, okay, if outlook equals to overcast, right? Then we can say play is yes. This is the simplest rule that I can create. by looking at the tree. Okay, if you build a decision tree and then if you try to convert into a rule set, you can actually create 5 rules. So we have look at the first rule. If outlook is overcast, we can say play is yes. Similar to that, if you come into the left branch, if outlook is sunny and humidity is high, we can say play is no. If outlook is sunny and humidity is normal, then we can say play is yes. Then if you focus on the right branch, if outlook is rainy and windy is false, then we can say play is yes. If outlook is rainy and wind is true, we can say play is no. Right? Those are the 5 rules we can generate after building the tree structure. Okay, good. So this is if you are using the first technique is if you start with the tree structure and then if you are building a rule set, right? That's one way of generating rules, right? So this is what I want to explain you with the example tree that we have built. So trees we can convert into rule set. So each path in the leaf becomes a rule. That means we had 5 leaves. Then each leaf we are getting a rule, right? But we can actually make it more efficient. So we are going to see how we are going to do this. So let's start looking at directly generating rules from data. Right. So we are going to use an algorithm called covering algorithms here. So what we are trying to do is we are going to generate rules directly. So we start with each class in a data set. For example, I can select generating rules for class yes. And then once we finish class yes, then I can go for class no, right? That's what we are going to do. This is called covering because we are trying to identify the coverage of the instances from the data set. Right, now let me explain with this toy example. Let's say we have numerical data set. We have 2 attributes, let's say X and Y. And if it is numerical data, then we can specify them as the points in the 2D plane. And let's say we have 2 class problem. Let's say some instances are recorded as B, others as A. So let's try to find generating a rule set for class A. So what do? You start with empty left-hand side and the right-hand side, your chosen class. So therefore, we will say if true, then class A. So we don't have any attributes or attribute values we have selected. So once you do this, what you are trying to do is you are trying to separate the data as much as possible. So when you create a rule set like this, we know that the accuracy is very low because we know that we have about 6 instances here and we have around like 20 instances here. So 6 divided by around 20. So accuracy is very low if you are creating a rule set like this. But if you can identify some place in the x-axis which separate A from B like this, so you can see some of the B's are here, we separate, and then all the A points are in the right-hand side. We can find a split point. So if you can split point, we can update my rule saying that, okay, if X value is greater than 1.2, then we can say class A. So if you calculate the accuracy again here, we have 6 instances of class A. Total be around like, let's say 12, right? So now accuracy is improved compared to the previous rule. So accuracy of this rule is better than the previous. Then what you do, you go in the Y direction. again, if you go into Y direction, you can find a place where it will separate A from B, like somewhere here. So that means if you say if the value is greater than 2.6, this part, you can see everything is classified as A. Accuracy is, okay, if you have 5 instances here, 5 divided by 5, that is 100%. So if you have 100%, we can stop at that point. So this rule actually covers these 5 instances from the dataset. And that's the basis for covering algorithm. We can generate rules to cover some of the instances. And if you follow the same procedure, you can create a set of rules for B's as well. And then when you get all the rules together, you have rules to identify A and identify B. So the basic idea of covering algorithm is, as I told you earlier, you are starting with one particular class. In my previous example, you observed that we have selected the class A, and we try to optimize the accuracy. But like we try to find the attribute, we have a bit of a problem here as well, right? How do you maximize the rule accuracy? It's like identifying an attribute. We need to find out the split point, right? So what we need to do is when you put up a new test, right, it should improve the overall accuracy, right? That's what we are trying to do here. So what happens? So we start with all the examples, and when you generate a rule, what happens? The scope will be limited, but the accuracy will be improved. If you keep on adding new terms, the tests, what happens? The coverage will be smaller, but the accuracy will be higher. And that's the basis for the covering algorithm. Right. So when you want to find the accuracy, we can define the accuracy like this, the maximum accuracy. So the number of instances, we can say the total number of instances will represent as T. We will take positive examples of the class, meaning that if you are selecting the class as A, we want to count how many A's are in the dataset. So that's what we call the positive examples. So the error we can get by reducing these two, and we are trying to maximize the ratio between the P by T. So if the P by T is 1, we know that it's pure separation, and we can stop at this point. Right. Now let me do a small example, right, based on the data set. So let me explain the covering algorithm with the contact lens data. But before we start, let me briefly explain about the data set. This particular data set is again about recommending the contact lenses. There are 3 classes. You can observe that there's a class called none, soft, and hard. So based on the age, spectacle prescription, astigmatism, tear production rate, the 4 attributes, we are trying to predict whether the contact lens is none, soft, or hard. So that was the problem given to us. Okay. So let's look at how we can actually use covering algorithm to create the rules based on this data set, right? Okay, let's start. So the first step is, okay, we have to first select one of the classes. So in this particular data set, there are 3 classes. we have none, soft and hard. So let's say we are trying to identify rules for class hard. So the first step is we start with empty left hand side, and then we are going to say recommendation is hard, right? And then in the empty, we can put like these possible tests. What are these tests? You can go through the data set. In the data set, we have 4 attributes: age, spectacle prescription, astigmatism, and tear production rate. These are the possible values. So for age, we have 3 values. Spectacle prescription, we have 2 values. Astigmatism, we have 2 values. Tear production rate, we have 2 values. So this is all. That means 6 plus 3, we have 9 tests. So let's start with the first one. If you put age young into the rule, meaning like if age is young, then recommendation hard. Let's say we are going to create a rule. If age is young, then recommendation is hard. Just check with the data set. How many instances are there with age young? So if you go back the data set, how many instances we have age young? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 instances, right? With age young. And out of these 8, how many instances will recommend the output as hard? You can see, right? We have 1 here, another one here. So there are 2 instances which recommends the lens as hard lens. So that means if you go back to the test, if you put age young, the accuracy will be 2 out of 8 because there are 8 instances with age young. Out of 8, there are 2 instances recommends the hard lens. So if you calculate the accuracies for all possible tests, this is the accuracy you are getting. So you will get 2 out of 8, 1 out of 8, 1 out of 8 when you have age. For spectacle prescription, we get 3 out of 12, 1 out of 12. Astigmatism, we are getting 0 out of 12 and 4 out of 12. Tear production rate, you are getting 0 out of 12 and 4 out of 12. Now I have a small question for you. Which one you are getting the best accuracy? Which attribute value? Which test gives you the best accuracy? So if you search, if you look at the accuracies, we are getting the best accuracy when you have 4 out of 12. We have 2 attribute values. Astigmatism no, and then tear production rate is normal. So that means you can select one of these 2, either astigmatism yes or tear production, astigmatism yes or tear production rate normal as the best answer. So let me move to the next step. So you will go to astigmatism yes, and then recommendation is hard. So this is our best rule now. What is the accuracy? 4 out of 12. Now, if you look at the data set, our original data set, we have 24. It will reduce to this number. Why? It will be 12 now. Why? Now we have a requirement. The astigmatism should be yes. So what do you do now? Again, you modify the rule. So you keep the astigmatism yes, and then you are trying to fit another possible test. Now this time, since we have already selected astigmatism, we left with the other 3 attributes. So you can see for age, spectacle prescription, and tear production rate, we have these tests. So we repeat the process and we calculate the accuracies, and these are the accuracies we are getting. Now we have to ask the very same question again. Which one gives you the best accuracy? So in this particular case, when you search the best accuracy, you will see that you are getting when you fit in tier production rate normal. And that is gives you the best accuracy. Now what happens? You can say the coverage. We started with 24. Then with astigmatism, yes, it down to 12. Now with this one, it down to 6. And this is what happens. So you add the rule, if astigmatism yes and tier production rate normal, the recommendation is high. But remember, the rule accuracy is still not 100% accurate, but we'll get 4 out of 6. We are getting about like 66%. Right. And then now we see the modified data set now. We have both astigmatism yes and then tier production rate is normal. So now we need to update the rule. So we can update the rule again, but this time we have used these two. So therefore we left with these 5 possible tests, right? So in this particular case, what is the accuracy? If you put age young, I'll go back here, right? When age is young, if you put it age is young here, what is the accuracy? If astigmatism yes and tier production rate normal and age is young, my question is, what is the accuracy of the rule? Is your modified case, for age young, you will get 2 out of 2. That is 100%. Here it's 50%, 50%. Again 100%. This is 33%. So these are the accuracies now we are getting. Now tell me which one you are going to select, which attribute test you are going to select as the best one. So when you calculate the accuracies, okay, we have 2 cases with the highest accuracy 100%, but this has more coverage. We have more instances. So therefore, this is what we are going to select as a final rule. So there's a tie between the first and the fourth. We choose one with the great coverage, which means the fourth one, right? So our final rule is, yes, if astigmatism yes and T production rate normal and a spectacle prescription myope, then we say its recommendation is high, right? But remember that this will cover only 3 instances. Originally, we had 24 instances. So 3, we have a rule. So we remove these 3 from the dataset. Now we have 21. You start from the beginning. So you start from the beginning like earlier with the empty left-hand side and for the hard class. And then likewise, you will find all the rule for the hard class. Then you go to the next class. There are 2 more, right? So you select the next 2 and then you count, you keep on doing this until you cover all the classes. So this is how the covering algorithm works. So this is called Prism algorithm. Let me show you how this is done in WEKA as well, right? So if you go to Explorer, and if you open up a file, let me go to the data folder. And if you go to the data, there should be a data set called contact lens. Here's the contact lens. Okay, here we have. Okay, this is the data set. You can go to edit and visualize. This is a data set. We have 24 data points. And if you go with each, you will see the separation. But if you go to the last one, that is a class attribute. You can notice that there are 5 soft, 4 hard, and 15 none. These are the classes. And if you select age, this is how we distributed, right? You see how the data is actually separated, distributed among the attribute values. Okay, I'm going to go to classify and I'm going to choose rules. Under that, this is called Prism. So select prism, and then I'm going to click start. And if you go here, these are the rules generated from here, right? This is the rules for all the 4 classes. You can see the first one for soft, hard, and then hard, normal. Okay, then, so not normal, it's none, and then none and none. So you can see the number of rules generated from the prism using the prism algorithm for the contact lens dataset. How many rules? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 rules actually generated by the prism algorithm. Right. With that, I would like to conclude the today's session. So what we have covered, actually, we have covered another set of machine learning algorithm. We started with 1R with numerical attributes, then decision trees, and we have just started with generating rules using covering algorithm. So you can actually practice, with the tools. So we have learned a new machine learning algorithm, trees and the prism. So there are some other data sets already available. Just check and try to generate the different models that we have learned. You can start with 0R, 1R, trees, and also the prism algorithm, and observe the outcome. So the next class, we are going to discuss more. We are going to discuss, there are a few more theory that I need to cover about the covering. Then we are going to discuss nearest neighbor and then naive Bayes. So hope to cover those 2 algorithms in the next class. Okay, then with that, I will conclude the session today.